Good afternoon, everybody. Can you hear me okay in the back? Excellent. Welcome to the final session of the day. It's entitled Breaking Down PFAS, Advances in Source PFAS, Fate, Transport, and Cross-Media Exposure Pathways. My name's Joe Applegate. I'm a senior principal geologist for Geosyntec up in Tallahassee, Florida. This is my sixth time of attending the PFAS conference. It's been a great 6 years, and hopefully we have number 7 either next year or the year after. Geosyntec's excited to be platinum sponsors this year, and want to thank Gene for continuing this wonderful forum. You know, I usually tell a PFAS joke each year, and I was so happy to see Tanya actually told one in the last session about, did you all hear that? Yeah. Well, I've got one more. You know, PFAS jokes are really hard to come by. Just try to Google one. You won't find very many. But once you find a good PFAS joke, it lasts forever. Most of the PFAS jokes are like that. Anyway, I'm honored to have three PhDs on our panel, so I'm excited to be on this panel. We do have a substitution though for our third and final one. So without further ado, I'd like to introduce Dr. Bagawandoss. He also goes by Dr. Doss for many of us that have been working with him for a year. I'm excited that he's here today to talk. I met Dr. Doss about 3 years ago at Florida Remediation Conference, and I was excited because he said he was starting up a new forensic lab. And I don't know how many do forensics in the room, but forensic labs are really hard to come by these days. And so I've actually had the pleasure of working with Dr. Doss on several complex PFAS sites in Florida. So without further ado, Dr. Doss.
Thank you. Thank you, Joe. So my question is, are we as human beings emitting PFAS? Because the theory is human population has 97 to 99% of the PFAS in our bodies based on our traditional practices in life. So I don't know that. And the compound list for PFAS in air is totally different from everything you heard today. So, and there are only maybe 2 or 3 labs in the United States of America, or even North America if I could venture, who does PFAS in air. But that's a very important component, is what it is. And you will see in this conversation how all of the methods you heard on PFAS coalesce together to collect air data. So with that said, I'll get started. And what that OTM stands for is EPA calls it Other Test Method. That's what that OTM stands for. And there are 2 methods on OTM. One is 45, which is an impinger liquid collection method from incineration or combustion activities. And then the air collection in canisters, just like you would do TO15, TO12, all of those, or TO3, it's a canister collection method. So once we go through the meat of the method, you will see how they try to equate it to TO15. So I have an agenda here. Basically, we'll go through some background stuff. And then another component is the NIOSH AIHA World, which is ACGIH, American Conference on Governmental Industrial Hygienists, are the ones who set the standards for IH monitoring activities. So they have introduced 3 PFAS compounds. So I've got a slide on it. I'm not going to dwell on it, but it is part of the air mechanism. But one is a liquid method. Like I said, the liquid methods coalesce to measure air data. And then we'll go through the methods, and then all about OTM-50, and then we'll combine OTM-50 with OTM-45 and how the sampling trains work. So once you see that, then it'll come automatically as to how all these methods combine. And OTM-50 is a different method compared to everybody else, is how it works. And then we'll talk about ultrashorts and how that comes in. And ultrashort method was, I had a poster last at FRC where we standardized that method at ASTM. It's now an international standard as of December, and ultrashorts are C1 to C3 PFAS compounds. And then the regular PFAS you hear about and measure are from C4 through C14. We never cared about C1 to C3, but they are abundant. So what happened was, in the realm of things, regular PFAS we were measuring went from 4,000 to 7,000 compounds. When you introduce the ultrashorts, it's like 7 million isomers is what's happening now. So that's what the context is for the ultrashorts. But it's also measured as component of air, as PIDs and PICs. PIC is product of incomplete combustion, and PID is product of incomplete destruction. So that's what it is, and you'll see examples of it, and the drivers for measuring PFAS in air. So basically, it's a list of 30 compounds. It's not part of your regular PFAS list. So you'll see that list. And then this method is not specific. They're related back to TO15 analysis for volatile organic compounds. And a lot of the references, the initial method published, is vague. So what we had to do when we developed the method for OTM-50 in our lab, we had to call EPA Research Triangle Park. They were very gracious to help us out, and that's how we were able to do the method. Then after that, they published a paper. That is more comprehensive than the method itself. So, and like I said, PICs and PIDs, I'll show you a picture on a publication in March or April of this year. It's a comprehensive paper in Science is where it was. And then we'll see what are the major PID emitted compounds. So this is a picture. So look at the red rectangular boxes. That's where the products of incomplete destruction come in from all these processes, or all the operations in a typical situation. So that's what we are measuring in OTM-50, is PIDs and PICs. And then the destruction technologies, thermal, closed vessel systems, and open vessel systems. So there are a lot of things. And PFAS can be destroyed. Incineration is getting perfected now compared to when it started. So it's more complete now than when we started a few years ago. And then plasma is the best one, but it's very expensive. And then the sonolysis is char combined with plasma is what sonolysis is. It's like 4,750 degrees C. When we started incineration, it was 900 degrees C. What are we doing, right? Because chlorinated compounds like dioxins, it's like 1,400 degrees C or so for 99.999 destruction. And carbon-fluorine bond is the strongest bond compared to carbon-chlorine bond. Yeah, I understand about the retention time in the furnace and all of that, but it still didn't cut it. That's why we went back to the drawing board on incineration. So here is another thing as to how depositions happen is what this picture depicts. Again, PICs, PIDs is what it is. And then volatility part, it's emergency response sites, firefighter training, and the exposures relating to that. But it is all in the context of C4 to C14. until OTM 50 came about, where the list of compounds are totally different. So ACGIH introduced these three compounds. So the first one is your regular PFOA. It's an ammonium salt of it, and we can measure it by 1633. And the other two compounds, PFBE and PFIB, we cannot even buy standards in an air matrix currently. Yeah, you can get liquid standards, which means you'll have to do some other technique other than OTM 50. So, which could be adsorption tubes, or the liquid collection samples. When you see the sampling train, it'll become obvious. So that's what ACGIH has published, and they have limits and everything like that. So analytical methods, GCMS, OTM 50 can be analyzed by GCMS, but we run it on a triple quad. There's no MRM transitions like other PFAS measurements. So that's what it is. And then OTM 45 is another air method, but it's just like a normal stack test. The tube coming out, you collect samples in impingers, just like you will for inorganics or organics, and then you take that water and analyze it. It obviously becomes 1633. And then ASTM D8591 is an adsorption tube method, if you will, like TO17 is what that is. And so you can measure fluorotelomere alcohols by adsorption tubes, as well as liquids as part of the C4 through C14 analyte list. And it's only like 4 compounds. And then ASTM D8628, that is the latest and greatest method where we measure ultra shorts, C1 to C3, which we don't measure in any scheme or any regulatory scheme currently. So this will become a very important method to account for the mass balance, like we talked about this morning, or earlier this afternoon. And then the ACGIH, and then OTM 50. So we measure those two compounds where there's no gas standards as non-targeted analysis compounds. So we look for those. And then this is the list of the 30 compounds, and you'll see it published in the OTM 50 method too. You can Google it up, you can pull it up. So here are all of these. And I highlighted trichloro-monofluoromethane. That is one compound which is found on the NIOSH list, is what it is. So it's already part of it. So then I went a step further to see about AIHA and NIOSH methods. These are all the fluorinated compounds listed in it. And so there's one compound which belongs to OTM 50. And they have limits for all of these fluorinated compounds. And then the stability of the OTM 50 30 compounds, it's very stable for all compounds up to 90 days and beyond, except for 2 compounds, CF4 and then hexafluoroethane. Those 2 compounds fall out on week 17. So week 13 goes up to 90 days. So typically, if you will, the holding times could be 90 days for the OTM 50 compounds. So this is a list of the MDLs and the detection limits, and the samples are collected in canisters. You'll see the sampling train coming up. And this is a chromatogram, right? So that big peak in there, that is carbon dioxide. So managing carbon dioxide in air samples specifically for the OTM 50 compounds is a very, very important step, because it could consume all the first compound and the rest of them coming up right after the carbon dioxide peak. If that peak broadens, those peaks coming up to 5 minutes will be consumed by the carbon dioxide peak. So managing that is an art. So OTM 45 list, it's a list of 48 compounds. It's typically the 1633 list and some added components to it. It's a long list, so I didn't even bother to put it up here. So 8628, that's the ultra shorts, and these are the compounds we measure along with the surrogate standards. So TFA is abundant in most places, and you'll see it in a lot of drinking water samples as well. So there's a lot of measurements which are going on right now on the TFA part of it. And then PFPRA, some labs can do it using 1633, but 8628 measures it perfectly. And then this is the fluorotelmer alcohols on adsorption tubes. And this is part of 1633, as well as 8691, which you saw. That's the desorption technique in adsorption tubes. So sampling methods, you can do it by XAD2 resin. You can do the desorption tubes, like I said in TO17, those types of tubes you can do. And OTM45 is the impinger method. And then they have, if you look on top, there is an XAD cartridge as well. So whatever escapes, it's captured on XAD and then extracted and analyzed, just like you would on a TO13 on the XAD2 resin. So that's what that is. And then Summa canisters is regular canisters like you would for TO15, TO12, TO3. So you can do 6-liter cans. So now people are adventuring into soil vapor samples for OTM50 compounds. So that's coming up shortly. So here's a sampling train. You see, if you will, the stack testing. Heated tube, you can put a canister on there, and then take that canister and analyze it for the 30 compounds. And then the next one is impinger, right? So now you can measure your regular C4 through C14, plus the ultra shots also from this liquid. So you can accomplish both using this impinger, and then you got your canister as well. So you got both the OTM50 and the traditional methods you do your analysis. This is what I mentioned about all of those methods you heard coalesce into the air. And then there's a duplicate can, just like you would do in a field for soil vapor stuff, where you have dual cans for collecting samples with a T and all of that. You can do the same thing here as well. So those are the sampling approaches you have. And also we have done projects where people take canisters just like you would on a TO15 measurement when they are doing spill response activities like AFFF foam spilling or some other activities. Then they can collect canister samples and analyze it in the lab. So these are examples in terms of the fluorotelmer alcohols and the volatility part of it. And also there are state-specific limits, like there are 4 states which have limits and guidelines in permitting processes. And it's like New York, Texas, Minnesota, and New Hampshire. I saw Hawaii recently doing the same thing. So if you look at the fluorotelmer alcohols in air, you'll see it in wastewater treatment plants and landfills. And then there's another wastewater. So you see the 6.2, 8.2, and 10.2. What we are doing is not capturing the 4.2 is what my guess would be. That's why you're not seeing it in wastewater treatment operations. It's probably evaporating out and depositing somewhere we are not measuring. And then this is children's bedrooms, right? Indoor air, and fluorotelmer alcohols predominate on this study. So stack testing drivers, it's incinerators, which handle AFFF foam. And then you have factories producing PFAS or polymers. So polymers, you have to be careful because there are unintended consequences on polymers. An example site is a site in New Jersey. They bought polymers from Japan. And they did not buy any PFAS components. But it so happened in the manufacturing process that it contained PFNA, and ultimately the groundwater was contaminated because of that. It's an unintended consequence of manufacturing polymers. And then factories using PFAS, and most of these are driven by PFAS measured in soil and water. So now you have the air and the ultra shots. Like I was telling people, 98% of the drinking water issues, or 98% of the compounds found in drinking water in Germany are ultra shorts, and only 2% C4 through C14. And we are not even measuring anything in North America. So in summary, it's complex analyses. So even though the method is on OTM 50 is based on TO 15, it's not that easy. And also CF4 measurements. So there are two kinds of instrumentation. One is cools and desorbs using concentrations and then desorptions by liquid nitrogen. So liquid nitrogen goes to minus 160 degrees C. And whereas another system technology exists where it goes only to minus 50 degrees. So you have to adapt to measure CF4 because it doesn't concentrate. So you have to do two different measurements for OTM 50 if you go with one technology versus the other. The liquid nitrogen technology will measure it in one run. The Peltier cooling method, you'll have to do two runs. So that's what happens. And management of carbon dioxide is a very important thing. Otherwise, you'll lose the front end of your OTM 50 compounds. And then it's not prescriptive. So you have to go through and talk to people who develop the method in order to get ahead in the game and make things work. And then the ACGIH TLVs for 3 PFAS compounds. So two of them, and one of them, PFIB, is what comes off when you heat Teflon-coated pans in your kitchen. PFIB is emitted from the Teflon part of it. And then ASTM 8591 fluorotelomere alcohols, that method exists for desorption tubes. It's not an EPA method, but typically what happens is if there's not an EPA method, then ASTM method can be used to solve your problems. And then ASTM 8628, it's ultra shorts with 5 targets and C1 to C3. And that's a very important method. And the Office of Drinking Water is talking about it now to come up with their own EPA method. But since there's no method, this rules currently. So that's what I have in a nutshell. So I want to acknowledge our SES staff, EPA ORD staff and Research Triangle, and then Mark's international staff, whose instruments we use. So that's what I have, folks. And I think we'll do the questions at the end.
That's great.
Thank you.
Okay, next we have Dr. Alauddin Khan. Dr. Khan's a senior environmental engineer with Leidos. I'm really excited to hear this presentation. It's always a challenge when you're doing soil assessment for PFAS, what your screening criteria are. I know in Florida we have leaching numbers and direct exposure, but if you were to use those ultra-conservative numbers, you'd have to excavate the whole site. So I've heard several presentations, but really looking forward to Dr. Khan's presentation today.
Thank you. Thank you. We have been hearing a lot about measurements, data collections, and my presentation is going to be what do you do with this data? How do you use this data to come up with some screening levels to say whether the site is clean or not clean, or do you have to do some actions to take care of the sites? So that's what my presentation is about, quantifying the PFAS compounds, how much you can leave it in the ground without causing any problems. So we are trying to find that. Okay, let me. So I'm getting familiar with this. My presentation will contain study goals, study overview, results, and finally conclusion and summary. The goals. What are the goals? The primary goal is whether what you have in the Vadose zone is going to cause any problem to the groundwater. So the groundwater pathway from soil is the primary goal. Why? To support the selection of appropriate mitigation strategies. Secondly, to assess the benefit and cost of developing site-specific screening levels versus EPA default values. And what we are developing, we have values from EPA, the screening levels, the default levels. So sometimes you can just use the default levels and compare against your concentration in the soil and say whether a constituent is a problem or not. So sometimes it may be useful only to do that and not do any further study. And sometimes it's different. You have to do the analysis. Why do you have to do the analysis? Because to provide practical and pragmatic guidance for PFAS investigations rooted in rigorous technical evaluations. And why do you need that? Because you want to help the decision maker, provide them with the numbers which they can defend. So you have sound science behind it. So that is why we need to do the rigorous analysis. I'll be presenting, this is for a site in the Midwest, and this is the example site. I'm going to present the data and the results on this site. The figure that you are seeing is based on EPA guidance, the conceptual model where you have the plan view and the cross-sectional view. So the plan view shows you the contaminated soil source and the direction of your plume in the groundwater, and the cross-sectional view shows you the source, how it is getting into the groundwater, and then migrating down gradient to the receptor locations. For this, you do collect a lot of data. You collect pore soil data, soil concentration data, pore water data, and groundwater data. You need all this data to make the analysis to find out whether it is going to be a problem or not. The first thing you need to do is when you have a site and you have a lot of soil samples, you have to analyze the data and come up with soil contaminated zones. How do you define the soil contaminated zones? I mean, using your soil data, look at the concentrations and compare against the EPA default values. And so anything greater than that, you can use that area to be your soil contaminated zone, or CSA we can call it, contaminated soil area. And from that, so for each of these soil area, then you will analyze and see what is getting into the groundwater by leaching through the, by percolating rainwater, leaching your soil and taking it into the groundwater. So that's the pathway you have to look at. And we used 4 methods for doing this. So this is like tiered approach. The first is EPA soil screening guidance, and it's simply the way the default values are estimated. EPA soil screening guidance gives you another method where you use site-specific data and develop your screening levels. The second one is linear regression using co-located soil and pore water concentrations. The third one is using sea soil and 8123D, 2 models. Sea soil is the leaching model, and 8123D is the transport model in the groundwater or the saturated zone. And the fourth one is modeling via PFAS leach. And PFAS leach is the recently developed model by Arizona University, and it is being used by, in the industry very well, and it has been accepted pretty well. So those 4 methods are used for coming up with the leaching concentrations in the Vadose zone. Now, how to define your lateral migration? What kind of dilution attenuation you're getting in the lateral directions? To get that, all those 4 methods uses different techniques. The soil screening guidance, it uses dilution attenuation factor without any attenuation. The soil pore water concentration method, it also uses dilution but no attenuation. PFAS leach, it has built-in dilution, just like the method 1 and 2. On the other hand, for sea soil 8123D, the dilution is calculated by the 8123D model in the saturated zone through advection, desorption, and attenuation. So if you make it a flow process, so the first square you see is the default values. From the default values, you are developing the revised SSL using EPA guidance, where you use the dilution attenuation factor and all the parameters, site-specific parameters. The next one is the pore water and soil concentration, co-located pore water and soil concentration data. Then we use the sea soil 8123D and the PFAS method. So all these different methods, the third column, we are refining the SSL. Then we are then comparing against the maximum concentration in the contaminated soil area or the CSA. So for each PFAS compound, you have the maximum concentration based on all the data you have for that particular CSA. And you are comparing that against the revised soil screening level. When you do that, this is an example from this site. We started with all the bold and not bold is all the compound that were detected for this site, for that particular site. And then we are comparing against the second column, which is the maximum concentration from that CSA, and the third column is the EPA default SSL. So when you compare, you see all the yes, which is bold, and there are 3 no's. So based on EPA default values, we rejected 3 of the constituents or 3 of the PFAS is not an issue. So we have to move forward with the remaining 7 PFAS compounds to do the further analysis. And I want to mention here that in case for your CSA, you see that based on the default values, all of them were no, then you would not have to do any further analysis. You do not have to go to the field and collect more data. So this would be a simple analysis. That would save a lot of time and money. Now the first method, which is the EPA guidance, your SSL definition is provided in the left with that equation, multiply by the DAF, which is the dilution attenuation factor, and the DAF is defined by that equation. Now I want to mention here that all these 3 different methods, they use this DAF. So this DAF is really very important because whatever you come up with, the SSL, from the left side, you are multiplying that by this DAF. And the DAF can be very high, can be small, depending on what parameters you are using. So collecting parameters, and what are the parameters it goes? Hydraulic conductivity, K, I is the gradient, D is the mixing zone thickness, Q is the recharge, L is the source length parallel to the groundwater flow. So it is very important to define your source area because L is dependent on that. It is very important to see what your hydraulic conductivity is in that source zone because K varies by orders of magnitude from one location to another location within the same site. So you may end up with a very high DF or with a very small DF, and your results will be not, good. You cannot rely on those kind of results. So it's very important that we all pay attention to the parameters that we use that goes into these equations. Now I just listed, for this site, based on the data we had, we came up with 4 areas, 4 CSAs, contaminated soil areas, and we had these parameters. These are the parameters that goes into calculating the DF. And I have provided in the last row the DF. See, for area 1, you have 42.9, area 2, you have 37.44, area 3, 29.35, and area 4, 17.91. This is for one site, but different areas. So they are quite different. And the reason is probably the size is different, the hydraulic conductivity is different right below the source. So those are the factors that is causing the DAF to vary. So going to the next step, see, we had 7 left from the default comparison. Now we are coming to the EPA guidance revised SSL, which is site-specific SSL. And now, based on the revised SSL, we have eliminated 3 more, and we have 5 more left. And again, we could stop at this step, provided all of them were no. But it's not, so we need to move forward. So let's talk about the co-located soil pore water concentrations, how we use that. We develop a log regression line. Log CW is pore water and log CS is the soil concentration. So using the data, site data, you develop a regression line, and from that you can estimate your M, the slope, and the intercept B, and then later on use those to develop a revised SSL. And the last equation is your revised SSL. And you see in that your B and M is estimated using the first equation, and the MCL, now the CW becomes the MCL times DAF. So DAF is again used here. And the reason why MCL is multiplied by DAF is because once the pore water gets into the groundwater, there is mixing. So that's the DAF we are using here. So based on these, you can come up with a revised SSL, and this would be the most reliable SSL because it is developed just using the data. And you have, this M and B, you can use those values provided you have a good regression line, which means your R square has to be acceptable. If the R square is not acceptable, you can come up with a very bad correlation, and your M and B values could be significantly off, and your SSL revision, revised SSL could be not an acceptable number. So we found out for our site, we took samples, but we did not take the samples exactly at the same time and exactly at the same locations, and none of the data we could use to come up with the revised SSL using this method. So we had to abandon this method in our analysis. The seasoil 8123D, this is a simple, seasoil is used, seasoil and 8123D has been used for over the last 35 years, and it is well accepted in the industry. And for this, all you have to do is define your soil zones by layers and input the data into the seasoil, then run your model and get your leachate concentration, which gets into the groundwater. You apply that leachate concentration into 8123D model that estimates your groundwater concentration, then back calculate that groundwater concentration to come up with a SSL revision. And PFAS leach is the same way. The only difference with PFAS leach is that PFAS leach accounts for the air water partitioning, and seasoil did not, the one that we used. But right now, seasoil also accounts for air water partitioning. So now coming to the results, the top one is the CSA1, and I'm showing the results for the maximum soil concentration we have used, maximum pore water concentration, and at the same time we are trying to see what the groundwater concentration is below the site, because that is very important. You cannot ignore, based on the leaching, you find that a contaminant is not a problem. But if you have concentration in groundwater, you cannot ignore that contaminants. You have to take it into consideration when you develop your remediation strategy. So we have all these three data, and then we have the seasoil predicted groundwater concentration, PFAS predicted groundwater concentration, and the revised SSL based on EPA, based on seasoil, and based on PFAS leach. And you see they are different. The first is site-specific SSL is slightly smaller than seasoil 81 to 3D predicted values, and then it's the value predicted by PFAS leach is much higher. But then you have to look at the maximum groundwater concentration predicted by all these different models. If you look at some of the numbers, you will see that sometimes I think PFAS leach is accounting for too much due to air-water partitioning factor, and thereby under-predicting the concentration in the groundwater. So that's what we found out based on the results for CSA-1 and CSA-2. But for CSA-3 and 4, I mean, the prediction is, if you look at the concentrations in the max groundwater concentration and the predicted by PFAS leach, they are quite comparable. So for one side, it is under predicting, but for the other side, it's quite comparable. So why is that? We are still trying to find out what's causing this, and I'm sure there may be something related to the site data, or maybe the plume has already migrated and the groundwater concentration we are seeing is in the down gradient concentration, and our soil source may not be, at the peak it is in the decline, it is diminishing, so that's why probably we are not predicting, but we don't know for sure right now. We are looking into that. In the next slide, I present too much data, too much information, just to see how they differ from site to site. The numbers, you see the SSL revision or the revised SSL number changes from site to site. CSA to CSA within a same site, it varies. Now, finally, so coming to the summary, the soil and pore water data is very important, and they can play an important role in defining your SSL revision. Usually, as I have mentioned before, that the SSL calculated by the EPA guidance is smaller than sea soil 81 to 3D predicted values, and much smaller than PFAS leach. Overall, PFAS leach provides much higher values for the SSL as compared to sea soil. So it's kind of less conservative. And I would recommend anybody using PFAS leach to make sure that they look at the data and use the data. Do not use the results blindly. We have to look at the groundwater data, the pore water data. If you look at the pore water data, is orders of magnitude higher than that is predicted by PFAS leach, then you would question that. So finally, all three methods, you saw their values differ by orders of magnitude from one method to another method. But we have to be careful in using those values. And we can say that site-specific SSLs probably provide a robust understanding of the leachability and risk to groundwater. But it requires extensive data collections. If you don't have data, it's really, the results are going to be erroneous and it may not be defendable. So we have to collect good data to get good results. And this is for everybody's understanding, and I had been talking while I was presenting about these things. I mean, there is a lot of uncertainty in any type of mathematical modeling due to the simplifications you use to define your geology. Then to define your contaminant distributions, you assume that everything is, using the maximum concentration, for example, for the soil, but you have smaller numbers all around or below or above, but you are using one number, which is the maximum concentrations. So there is a lot of uncertainty added to this kind of analysis. And the recommendation is, mathematical model results are most effective for decision making when key assumptions and limitations are clearly understood and acknowledged. So that is key to this kind of analysis. That's all I have to say. So I used all your time.
There we go. Thank you, Dr. Khan. That's a great presentation. Last but not least, we actually have two co-authors here from Aquatech. Dr. Ronnie Erlitsky is in the room today, but she wasn't able to make it, but now she is here. So Devesh Mittal, who's the Vice President of Environmental Services with Aquatech, is going to talk on navigating complex chemistries and PFAS remediation.
Thank you. Good afternoon. Thanks for staying for the last session. It's between you and the drinks and the snacks. As was mentioned, I'm not Ronit. She's here. We had a scheduling mix-up, and we were trying to figure out who's going to make it. We both made it, so that's a good part. And but yeah, I drew the short straw, so I'm presenting. And I'm not a PhD, so I'm not as smart as Ronit, but I'll try to step up so that you don't feel getting shortchanged. So with that, I'll get started. We're going to talk about the complex chemistries and PFAS, and I think some of the presentations earlier on were very helpful, and I think I'm going to be able to build on those to highlight some of the things that were mentioned, and hopefully we can connect the dots. A quick word about Aquatech. We are a 45-year-old water and wastewater treatment company, privately held, globally present, doing a variety of things, 2,000 plus employees, about 500 plus million in revenue. We're privately held, so we never declare what our true revenue is, based out of Pittsburgh. That's our global footprint. We operate a lot of R&D labs, variety of labs. We do a lot of technology research, and we focus on technology-based water and wastewater treatment. And as a result, we are present in all these segments. We have 25 family of patents, over 125 patents. And we do a lot of research and development, develop new processes, and then we apply those processes across industries. And so that has worked very well for us. So a quick question. Is PFAS the most pervasive molecule in the environment? Show of hands. Nobody? That's a good one. It was a trick question. I think the most pervasive molecule in the environment is water. But since we contributed and commingled the PFAS into the water, it has become pervasive. I love this picture. This has been put together by AWWA. Credit to them. It kind of shows how the contamination of the water streams and water bodies happens through the discharges that occur. And I'd like to make two key points. One is that the water that we look at and use is contaminated with a variety of different PFAS chemicals that come in from a variety of point sources. So a given region could have very different matrix of PFAS in the water. So that is one. The second point is that when we are drawing that water or wastewater for reuse or for drinking, the entities that are being made responsible to treat that water are essentially passive receivers. And if we keep moving the PFAS by removing it and then putting it back into the environment, we're never going to get rid of it. We're going to continue chasing our tail. So it is important that we start eliminating that from the environment by destroying it. And it is a bigger challenge to destroy PFAS in large bodies of water. And so one of the things that can be done is to look at point sources upstream and treat those point source discharges for PFAS so that those PFAS compounds don't enter the larger body of water. I know it's not a simple thing. There are a lot of issues involved, and there would be a lot of different point of views. But at the end of the day, if we don't do that, then we'll always be looking at removing PFAS from a very large body of water. So these are the key segments where we feel that point source discharges happen, water treatment, wastewater treatment, federal facilities, industrial, aviation, food and beverage, semiconductor, chemicals, textile, landfill. So some form or the other of the waste emanating from these business segments ends up as a point source discharge. So how do we deal with it? I think everybody talks about a particular technology, how they've tackled PFAS. Our position is that it requires a combination of technologies, and with our experience in water and wastewater treatment, we have looked at combining those technologies to provide the most efficient and cost-effective way of solving the PFAS for a given situation. So we have put together a technology portfolio that we use, and we have broken it down into three categories. One is the removal, which is simply your media. You're using ion exchange, GAC, novel sorbents. You essentially absorb the PFAS onto the media and then dispose it off, whichever way is conducive. You're not necessarily getting rid of the PFAS from the environment, you're just basically recycling it, but achieving your specific purpose. The second category we have is the separation and the concentration, where we separate the PFAS and we concentrate it into a smaller volume. And by doing that, we can really focus on that small volume. Either we can send it to a disposal well, we can sequester it, And what we choose to do as a company is to basically destroy it. And we use a combination of ultraviolet, electrochemical oxidation, and we have a variety of technologies that we put in a sequence that is most effective for a given situation. So that's our technology portfolio. And we, in order to assess which path would solve the problem most efficiently, we have invested a lot of money in putting together an applied testing lab in Pennsylvania. It is capable, it has benchtop, pilot, and field scale units associated with all the technology portfolio I showed you. And one of the advantages of doing that, this is the view of our PFAS lab. So not only do we have the equipment to process the PFAS, but we also have on-site analytical. So we use the CIC method, EPA 1621, which Tareen talked about, and we also have the LCMS-MS. There we use ASTM 8421 for speciation. So in lieu of 1633, it provides 44 compounds, and it is a little bit simpler because it's a direct injection method. So we prefer that, it's faster for us. So I will show you some results, and then I'll tie what Tareen was presenting. I think I found her presentation to be very relevant, and I'll be able to show you some of the things that she talked about. So this is an example of our lab testing data. So this is on an actual landfill leachate. There are a lot of data that is presented specifically on specific compounds, but we have the data here, which is on an actual landfill leachate. This is from a landfill in Minnesota. The landfill was foam fractionated to convert into a concentrate, and the concentrate is what we took to the lab and conducted electrochemical oxidation on it to destroy the PFAS. Now you'll see there are 4 lab trials we conducted on it. Because of the equipment and the speed at which we can conduct tests within the lab, typically any given sample we can apply test it in a matter of 2 weeks. Here we were able to do these 4 tests in a matter of 1 week, and I'll tell you the story of these. Now the first trial we did, we found some very weird results. We saw a significant increase in short chain, and that is the trial number 1. You can see some high peaks there, and we were very surprised. So we brainstormed and figured out what was happening, and we were able to control some of the parameters and make modifications to our test, and then we were able to prevent the formation of short chains as the process was going on, and we were able to get significant destruction, and we could get repeatable results. So we not only try do an initial trial to see how the wastewater behaves, but we then also do an improvement trial, and then we do repeatable trials. The advantage we feel of doing the lab testing and the predictive testing is that it is fast, it is cost effective, and you can eliminate a lot of different scenarios that may not be beneficial to the effort. And by doing that, we can then go into what we call the confirmation testing on site. I know a lot of utilities and a lot of customers prefer to see the trial being conducted in front of them on their site. By doing the predictive testing in our lab, we are able to eliminate things that would not make sense, and we focus on the things that would really need to demonstrate in front of the customer. So we By doing that, we reduce the cost of doing the field testing, and we also make it fast. And so this is a great example of how by doing the lab testing, we were able to optimize, and now we are ready to do the confirmation testing on site. Now, she did talk about how the chemicals break down and how they behave. There are two chemicals here which we were not able to get very good destruction on. I think one was the PFBS, and the other one was HQ115. So landfill leachate is one of the most complex wastewater streams you will get, because we use a lot of products that use PFAS compounds, and then we pitch them in the landfill. And over a period of time, that PFAS ends up in the leachate. Every landfill has very high quantities of PFAS in it. And there are about 2,600 operating municipal solid waste landfills, and I would say 70% of them in areas where there's precipitation would have PFAS in their leachate. And it changes, depends on the weather, climatic conditions, how much of precipitation was there. So it's a very variable type of wastewater. Also, it depends if products change, they change the use of specific chemicals, then those will change the nature of the leachate. Now, in this, one of the things that I think Tanya talked about, some scaling. We did see some scaling because some of the divalent ions, they can coat the electrodes, and so we had to take some pre-treatment steps to prevent that scaling. And that was also very helpful to do these quick tests, so we could check out how we solve the problem scaling and get more efficient. So this is a very good example. This also shows how some of the compounds behave during the test. The other test I wanted to show you was we did the destruction of AFFF. This is a mil-spec military specification, 3% AFFF. So 3% means it is one of the most concentrated AFFF. So for using it as a firefighting foam, you use 3% of this and 97% water. And we diluted it a little bit in order to help the destruction process. And we use the AOF here in order to do the testing, and then we did the speciation on the initial and the final. And this kind of shows, because we are mostly dealing with longer chain compounds in the beginning, so AOF is a very good criteria to do the testing. It shows how fast the degradation happens, how the compounds that are caught in the AOF testing are degrading, and you will see a few peaks there and a few dips. Those are not outliers. They basically show how the TOP, the precursors, break down, different chains break down, and so it's a very complex chemistry, and everything that she mentioned during her presentation is visible here. That's essentially how it happens. So initially, when we started doing this testing, we were also surprised why the PFAS or AOF is going up. But then we kind of got smart and understood that it is the organic precursors which is breaking down and creating more absorbable organic fluorine measurable compounds. Eventually, the destruction goes down all the way. And if you look at the initial and the final, you will see that some of the compounds went up. So if you look at PFP-RA, it went up from 83 ppb to 700 ppb. So that also happens. So the breakdown and the destruction is not perfect. So if anybody says it's perfect, it's not. Now we have a solution for that. We use a multitude of electrodes. So in the first phase, we use one variety of electrode. Then in the second step, we can use that. But because now we are dealing with a very small quantity of PFAS mass, we can have a very, very efficient second step where we can destroy that. So this kind of shows how the chemistry breaks down, how what she talked about, the different compounds, total organic precursors, the difference between AOF and speciation, how those correlate. Initially, we have seen that the AOF values and the speciation summation tracks very well because we are mostly dealing with long chain compounds that are caught up and measured in AOF. But as the destruction happens, the AOF becomes less relevant and the speciation becomes more relevant. Now, all the data that we generate doing this is very scalable because electrochemical oxidation is based on the electrode surface area and the energy we provide through that surface area. So if we have good results for a particular size, we can scale it up to build a commercial unit, which is exactly what we are doing. This is a different wastewater. This is from an airport. So this is part of the PFAS AFFF replacement program. There is an effort to remove the fluorinated AFFF and replace it with what is termed as green AFFF. And as part of that effort, they drain the AFFF and then wash the tanks, and that generates a lot of wash water. That is not as concentrated as the AFFF, but it still has a significant amount of PFAS in it, most likely in the range of 130 ppm to about 300 ppm. Here also you see, we see some peaks. And these results are not outliers again because we did the test repeatable, we did number of times and we saw a similar trend. So there is something going on in the chemistry that breaks down after a certain time. The organic precursors creates more PFAS or measurable, AOF measurable PFAS till the time it goes down. So here also we saw the good results. So key takeaways, PFAS impacted water streams have very diverse characteristics, and so one size doesn't fit all. We have to look at what is coming in, what is the reason for that water being impacted, what all different contaminants came in, what is upstream of that receiving body, what point sources impacted it, and that is how you align the treatment needs. So most utilities that we talk to, when we broach the subject of them being passive receivers and what they are doing to look at the upstream point source discharges, they smile, and that is exactly what they're doing. They're going and talking to, because there's no regulation against discharging PFAS at the moment, most of the time it is monitoring only. So the utilities are now beginning to go and talk to the point source discharges. And those point source discharges are much easier to treat now. Different industries, different chemicals. So one size would not fit all. And what we do in the lab is to basically align the treatment needs and figure out how the compounds behave differently, and do the predictive testing so that we can eliminate things that would not bear results and not spend time and focus and money on that. And then that way we get to the confirmatory test. That is what's going to be used for a full-scale setup on the commercial side. So that's my presentation. Thank you so much. Appreciate it.
Very good. Thank you for that extensive presentation. We really appreciate it. Now we're going to open it up to questions and To the audience, have any questions?
My question's for Dr. Khan. Just curious if you contemplated SPLP testing, or if you didn't, do you have any experience with it with PFAS? And is there complications with it, or is it relevant?
Can you hear me? We haven't done SPLP testing, but we are also thinking of that. So I don't know whether there will be any complication with that or not.
Anybody else? Anybody else?
I've got a couple. Dr. Doss, I was curious, two questions about the PFAS in air. Does EPA have any regional screening levels or screening criteria for PFAS in air, or are they developing those? Or
It's just those states which are looking at. It's just the state part of it where they have listed recommended levels and use those in permitting obligations.
for permitting?
Yeah.
I
yeah.
see. So
It's a guidance thing.
there are some guidance
Yeah,
there.
yeah.
Are the units in nanograms per, what are the units? The
Yeah, it's basically PPT levels.
PPT level?
Yeah.
Okay,
Just like the normal measurements.
gotcha, okay. Let's see. For Dr. Khan, I was curious. It looks like you use multiple methods for trying to determine what levels are appropriate and safe for soil. Did you do any SPLP leaching site-specific? Oh, also, I was wondering for your pore water, did you collect those with like lysimeters?
Yeah,
Yeah.
no, we did collect lysimeter samples for the pore water, but we did not do any SPLP analysis.
Okay.
The problem with the lysimeter samples that we collected and the soil samples we collected, they were not at the exactly same locations. So that was the main reason that we could not use the pore water soil, co-located soil data for developing the revised SSL. And that would be the best way to go. So from now on, I mean, for other sites, we are making sure that we collect the data from the same locations and at the same time.
Gotcha. The PFAS leach model, is that an EPA model?
No.
No.
It is developed by University of Arizona,
Uh-huh.
and so it's in the early stage. They have, I mean, 4 tier models. Tier 4, 3, 2, 1, 2 and 1 are not ready yet. 4 and 3 are, I mean, people are using it, but it has not been approved by EPA yet.
Is it available for other practitioners?
Pardon?
Is the PFAS leach model available for other practitioners?
Yes,
Yes.
it is available to everybody.
Just go to the University of Arizona?
Mhm.
Okay, great. Thank you very much. Any other questions for the presenters today? If not, I think we're adjourned, and happy hour is calling. We've got about 40 minutes before it's...
Everybody will help me give applause out for our panel. Thank you very much. And as Joe said, happy hour is next door. We do have our poster presenters that will be by their posters, so I encourage you to see what research they're working on and enjoy the happy hour. Have a beer for me.